Hi, I am Dr. Samir bin Osman, and in this video we're going to talk about the principles of computer science. So computer science is the study of the computation of information and the automation of the computation and the processing in computer systems. So information is generated spontaneously in the universe every time atoms and molecules interact within human organs, or every time humans interact with each other, including economic interactions between humans and their devices, and between humans and their environment, and within the ecosystem, etc. So every time there's something that happens, there's information that spontaneously exists. So capturing these types of information into data and automating the processing of this data to get the insights that help us facilitate our daily operations is the field of computer science. So this science was born from the discovery that logical operations could be carried out by electrical circuits. And so interpreting the resulting currents as results of arithmetic operations is the basis of computer science. So computers, they use complex circuits that are called hardware. They're designed to be flexible enough to perform any combination of computations, and the way to configure or program them is called software, which enables users to produce various complex calculations or computations that are critical for the functioning of modern industries and devices. So let's talk about each one a little bit more. So let's start with hardware. So computer circuits are organized into components that specialize in either processing the actual computations, such as central processing units or CPUs, graphical processing units or GPUs, etc. And they get integrated into a holistic circuit, which is called the motherboard. And then the motherboard also will contain the components that will store the data inputs and the results of these computations, which is called the memory, as well as components that allow us to interact with the machine, and they're called interfaces, such as display screens, keyboards, mice, microphones, speakers, etc. Computer systems can be standalone, ranging from like personal computers, tablets, phones, to large supercomputers and data centers, or they can also be embedded into other devices, such as embedded in home appliances, embedded in cars, embedded in planes, rockets, satellites, etc. So the number of computers is not just what you see, it's beyond what you see. And in order to increase their collective power and integrate them into larger, let's call them superstructures, most computers are now joined either via data cables or wirelessly to form computer networks. And those networks will be managed by specialized, let's call them hub computers, which are called servers. And these servers are further connected mostly by data cables between them to form a global internetwork, which is called, for brevity, the internet or the web. So that's kind of a little bit of an overview of the hardware. Let's talk a little bit more about the computer software. So although the computer hardware significantly accelerates human computation, the methods of conducting repeated and or conditional computations, actually they pre-exist computers by a long shot, and they're called algorithms actually. And those methods were discovered by the Muslim scholar Al-Khwarizmi, and they actually given the name to the process itself. So Khwarizm gives algorithm. So these were like discovered centuries ago. So those methods are actually translated into computer readable format, and that computer readable format is what we call the code. And that code is written in a programming language. So languages will range from low-level computer circuits instructions. So basically they open and close computer circuits. So they're like very low-level languages, like the assembler that you can see here, a screenshot of. Or they can be higher level languages that will translate or compile more integrated instructions into one. So for example, it could be operating transformations on numbers, ordering lists of names, etc. And so these go into higher level machine instructors, and thereby enabling the programmers to produce elaborate code more efficiently. So they don't have to do like, smaller steps. They can just be grouped into kind of one sentence, one instruction that does a lot of things. And so these higher level languages, they're a lot more efficient at producing the results, but they become less flexible because you will have less choice to do. And so as they become higher and higher levels, they will become more and more specialized or more tailored for specific applications. And so you will have programming languages that are more focused on web design, more focused on maybe mobile phone programming, or more designed or for data science, such as Python, as you can see here, or others for like industrial equipment programming, etc. So the idea here is basically the higher level, the more specialization, which means that the software engineers, they need to decide what's the best language for the application that they wanna have. Now, how does programming work? What are the principles that are involved in programming itself? So programming involves 4 steps that are consecutive. Let's start with problem recognition, which is basically you need to understand the problem that you're trying to solve before trying to solve it, which means understanding what the problem is, what the challenge is, and what do we need to resolve it. Then it goes into problem definition, which is basically what are the inputs that we need, what are the processing activities that we need, and what's the output that we need in order to solve this problem, as well as identifying multiple ways of solving the same problem to pick the fastest one or the simplest one, etc. So once we found the best method to solve the problem, then we're going to design the logical steps that the program must follow to solve the problem. And then we're going to choose the language that's most appropriate to write the code in. And then the last step is when the algorithm that we designed is translated into code. And so this is kind of let's call it the steps of traditional programming steps. However, more and more there is kind of another pathway that's becoming more and more prevalent, which is machine learning or artificial intelligence. So at a higher level than even programming, instead of dictating a series of static steps to follow, these novel approaches, they produce algorithms that are fed data inputs with known results. And so they're trained on them. And so the algorithm knows what the correct result is, but we don't tell it how to get there. And so the algorithm will actually generate itself the intermediary steps that it needs. And then when it gets there, it compares the result it obtains to the results in its training set. And on at first, it's going to be off by a long shot. And then it's going to adjust itself in a dynamic and iterative way many times, and every time it gets closer and closer and closer until it gets really kind of good at getting the results that we trained it on. And once we do that, we can give it new data sets, and then it's going to give us the results that we need on these new data sets. And this is called machine learning, and it's much more efficient, especially at problems where there's a lot of variability, so constantly changing types of computations. For example, recognizing faces, as you can see here in this image here. Faces come in all different shapes and forms. The image also will be front facing, it could be profile facing, and if we're talking about videos, the lighting, the conditions, etc., like a lot of variations. So machine learning is becoming very good at solving these problems. And it's actually now developing so rapidly that it may become the dominant approach for programming in the future. So with that, in order to program, we need to have data, and we need to organize the data that we have. So how do we do that? So data is organized into large interconnected, let's call them tables. And these are called databases. And they reside mostly in servers, and they enable the storage, the combination of data, as well as the correlation of multiple types of data. So you can correlate names with addresses, you can correlate names with images, you can store videos, financial transactions, medical information, geographic locations like in Google Maps, etc. And any type of data that you can think of, it can be stored and will be stored in databases. And so the data can be added, it can be retrieved from the database, and it can be interlinked, so you can link multiple types of data in a database or between databases using specialized database programming languages such as SQL, SQL. This is kind of one of the main languages for dealing with databases. It's not the only one, but this is just one example. So when new data is added to the databases, there's one principle that's very important. the data must have the same organization and naming convention. Because, so for example, if you're calling the name column name, you cannot just add more data, and in the new data table, it has, instead of name, it has customer name, for example. So this naming convention has to be the same for all data that you're going to put in. And any discrepancy in these attributes and conventions in naming and the way the data is organized, the way the data is called, will reduce the precision of the data and the results of the computation. That's what we call garbage in, garbage out. If you have garbage data, well, anything you're going to process is just going to give you more garbage. And so that's why it's critical to have what we call data governance to ensure data consistency and quality. Now that you have the data, how do you send it, between computers and between networks of computers, etc.? So now we go into data transmission or information theory. So for data to be exchanged, it must be converted into electrical or electromagnetic signals. And so to accomplish this, there are complex approaches, especially mathematical approaches, that have been developed to translate data into basically variations in electrical waves or photonic or wave characteristics. So it could be changes in wavelengths, changes in wave amplitude, changes in wave frequency, etc. And this process, moving from information to electromagnetic waves, is called encoding. And then this electromagnetic wave will be sent through wires or wirelessly, etc. And then it will be received by antennae or like on the other side. And then it will have to be translated back into data, and that we call decoding. And you can see here in the image we have like zeros and ones as data, and they will be converted into waves, and that's kind of encoding, and the reverse is decoding. So to prevent the inevitable signal deterioration while in transit, because when you go wirelessly and wirely, you're going to lose some of that signal in transit. And so there are many mathematical approaches that are used to restore the data that's been lost and to fill basically the missing gaps. They're even using now machine learning to guess what parts have been lost and to restore them. Also, more and more data needs to be processed and sent now, especially with high definition videos, streaming, etc. And so the size of the data is becoming a big problem. And so sending the data efficiently requires more kind of ingenuity. And one approach to send the data efficiently is to simplify the mathematical structure of the data, for example, by grouping redundant data elements together and abstracting them and other forms. And this is called data compression. So the data is compressed and then sent, and then when it's received, it's decompressed and then leveraged. Now, in order to protect sensitive data, computer scientists developed mathematical approaches to basically scramble or encrypt the data upon its transmission and only allow its reconstruction or decryption upon receipt by the receiver who has the decryption key. So what is this key? And what is the encryption actually? So the encryption is basically asking the computer to find the solution of mathematical problems whose resolution cannot be accelerated even by computers. And these problems are called NP problems, such as, for example, finding multiples of prime numbers, So these things you cannot infer them. You have to just try and error by trial and error, just for trying them. And the decryption key is basically the solution. And so whoever has the solution can just decrypt the data. Whoever doesn't, it will require them to try one solution at a time amongst hundreds of trillions of possible ones, which will take them basically ages in order to find the right one, which makes it extremely unlikely to be resolved by malicious actors or hackers. Speaking of hackers, so those hackers will seek other means of accessing this sensitive data through either making malicious programs that are called viruses that exploit vulnerabilities in computer systems to copy themselves into the target computers and then open what we call backdoors for the hackers so that they can access the data before it gets encrypted. So that way they don't even have to fight the encryption. They also use other means to get to the sensitive data they want, which is called social engineering, which is basically exploiting the human flaws in the system, such as impersonating employees of a certain company and saying, I work for this company and I need this data now. I have a meeting. Can you just send me the data, etc. And then the person just kind of sends them the data without knowing that they're not even employees of the company. So all of these are like types of exploits that are called social engineering. So like human flaws, not computer flaws. So to counter that, cybersecurity organizations, they devise what we call antivirus programs. And those antivirus programs that seek basically and destroy programs that cause either known or unknown suspicious behavior. And they also regularly patch any discovered vulnerability in the complex systems. However, because the computer software is increasingly complex, well, those vulnerabilities will always exist. And so cybersecurity is a continuous game of attacks and defenses, and defenses to attacks, etc., etc. So it's a continuous war, or it's like a continuous battle between hackers and anti-hackers. So let's finish this session on computer science by some of the applications, current and maybe future, of computer science. So the applications of computer science are basically only limited by our ability to, like I said in the beginning, automate and accelerate useful decision making from the information that's spontaneously generated in the universe. And since there's a lot of information that's generated in the universe, there's a lot of opportunity for computer science to be applied. And so for now, in health, it would allow probably in the future the prediction of diseases, the diagnosis of the diseases and the treatment outcomes for specific patients. It allows currently the acceleration of drug discovery. In economics, it enables the fast transactions, automated transactions, financial transactions, as well as movement of products in the supply chain, prediction of the supply chain performance, or products that will be in stock soon or needed soon, etc. Tailored marketing that's tailored to the individual. In manufacturing, it enables the automation of repetitive labors through robots, and robots are basically, half of them are mechanical and the other half is software. And then in transportation, it enables the partial automation of plane piloting. That's what we call autopilot. And then car driving increasingly now. And due to the significant impact of computer science, it's actually defining a new industrial age that we call the information age, which is only actually in its infancy and will dominate human civilization in the future. And with that, it's the end of the video on principles of computer science. I would welcome your comments. Thank you so much, and I will see you in the next video.